We know that if E and F are two events in same sample space S, then the conditional probability of event E given that event F has occurred is given by the probability of E given F is equal to the probability of E intersection F divided by the probability of F, where the probability of F is not equal to 0. This implies that the probability of E intersection F is equal to the probability of E given F multiplied by the probability of F. Similarly, the conditional probability of F given that event E has occurred is equal to the probability of F intersection E divided by the probability of E, such that the probability of E is not equal to 0. Now, F intersection E is equal to E intersection F. This implies the probability of E intersection F is equal to the probability of F given E into the probability of E. From 1 and 2, we get the probability of E intersection F is equal to the probability of E given F into the probability of F. This is further equal to the probability of F given E into the probability of E. This is called the multiplication rule of probability. Let's now look at an example. Consider a pack of cards. Two cards are drawn one after the other without replacing the first card back into the pack. Suppose the first card drawn from the pack is a king, and the second card drawn is a queen. Then, what would be the probability of the event? Let K and Q be the events of drawing a king and a queen card, respectively. As we need to find the probability of drawing two cards one after the other without replacement, we have to find the probability of K intersection Q. Now, there are 4 king cards in a pack of 52 cards. So, the probability of drawing a king card is 4 divided by 52. The card drawn is not replaced. This implies that the number of cards available for the second draw is 51. Thus, the probability of drawing a queen card, given that the first draw is a king card, is 4 divided by 51, because there are 4 queen cards present in 51 cards. From the multiplication rule of probability, we have the probability of K intersection Q is equal to the probability of Q given K into the probability of K. Substituting the values of the probability of Q given K and the probability of K in the rule, we get 4 divided by 663. Therefore, the probability of K intersection Q is equal to 4 divided by 663. Hence, the probability of first drawing a king card and then a queen card is 4 divided by 663. This multiplication rule can be extended to more than 2 events. For example, with 3 events E, F, and G in sample space S, the multiplication rule is defined as the probability of E intersection F intersection G is equal to the probability of E into the probability of F given E into the probability of G given E intersection F is equal to the probability of E into the probability of F given E into the probability of G given EF. Let's consider an example. An urn contains 12 red balls and 8 blue balls. Suppose we take 2 red balls and then a blue ball one after another without replacement. What would be the probability of the event of taking 2 red balls and a blue ball? Let R be the event of taking a red ball from the urn. Let B be the event of taking a blue ball from the urn. The total number of balls available in the urn is 12 red balls plus 8 blue balls, which is equal to 20 balls. First, a red ball is drawn. And since there are 12 red balls, the probability of taking a red ball is 12 divided by 20, which is equal to 3 divided by 5. Since the ball drawn is not replaced in the urn, 11 red balls are now available, and the total number of balls is 19. Now, the probability of taking another red ball is given by the probability of R given R is equal to 11 divided by 19. Since another red ball is drawn, the total number of available balls in the urn is 19 minus 1, which is equal to 18. Therefore, the probability of taking a blue ball with the condition that 2 red balls have already been taken is given by the probability of B given RR. This is equal to 8 divided by 18, or 4 divided by 9. From the multiplication rule for 3 events, we have the probability of RRB is equal to the probability of R into the probability of R given R into the probability of B given RR. Substituting the values of the probability of R, probability of R given R, and the probability of B given RR, we get the expression as shown. On simplifying, we get 44 divided by 285. Therefore, the probability of RRB is equal to 44 divided by 285. Hence, the probability of taking 2 successive red balls and a blue ball is equal to 44 divided by 285.